So this lesson is essentially a lesson where you are learning about 5 different theorems, and they have to do with similar triangles. And so you see the angle bisector proportional side theorem, a triangle proportionality theorem, the converse of the triangle proportionality theorem, the proportional segments theorem, and the triangle mid-segment theorem. So we're going to go through real quick. Those are the main ideas, is making sure you understand what those theorems actually say and then how they can be used. So to begin with, you have an exercise in here where what they're going to have you do is they're going to have you draw, it says draw a line parallel to AB that goes through point C. So in essence, what you're doing is you're drawing a line through here, right, through C, and it has to have the same, it has to be parallel here, okay, to AB, but it goes through here. So that what you end up with is something that looks a little bit like a rectangle, right? And you would be doing that down here on this part of the page, okay? And then you're going to start to fill in the proof of the angle bisector proportional side theorem. And then the idea with this proof is that essentially, let me go through here and just kind of explain it to you. And you're going to have to probably watch this a few times and then go through it. But the first thing is what we know and what was given is that this segment is bisecting that angle. And so what that means is that this angle, which is BAD, is congruent to this angle, DAC, by the definition of a bisector, an angle bisector. If it's bisecting it, then they are congruent. And then you have a parallel line, and then what happens with that parallel line, if you extend AD down to it, you're going to realize that that's going to form another triangle down here. So you're going to come way down here with that parallel line, and you're going to make this line here come down. And then what you have is because they're parallel lines, you have interior angles that are congruent. So this angle that's going to end up down here is going to be congruent to this one. Those are alternate interior angles. Remember, when you have parallel lines here and then a transversal that goes through them, that the alternate interior angles are congruent. So that's BAD. And if you name this point down here E, and that's what it says, you know, you're extending AD and you're extending this line that comes down here until it hits point E, that CED and BAD are alternate interior angles. And that is actually line 4 in there on that proof that you're filling in. Then you have this idea that because these angles are congruent, DAC and DAB, and these angles, BAD and DEC down here, since those angles are all congruent, then therefore this angle and that angle have to be congruent as well. And so then what happens is you end up with, let's see, these sides. So if you look at this big triangle, which would now be AEC, then this side AC is going to be congruent to this side CE on this big triangle. And that's because, if you remember, we talked about the Hinge theorem a little bit, the idea that this angle, if it's open that wide, right, and this angle is open that wide in a single triangle, so those are sometimes called the base angles, then the sides across for them are going to be congruent. And those base angles, we call this theorem the base angle theorem, the base angle theorem. And what the Hinge theorem said was, remember, that the angle in a triangle, the angle that is largest will be opposite from the side that is largest. And the reason I bring that up is because if the angles are the same size, then of course the sides opposite them have to be the same size as well. So now you've basically proven, you know, this side and this side are congruent. And then what you're going to do is you're going to, you know, which means that their measures are the same. That's line 7. And then what you're going to do is you're going to go with the alternate interior angle theorem on this angle right here. So you're going to say, let's see, we have another pair of alternate interior angles. So this would be DCE. This angle that would be right in here is going to be congruent to this angle right here. So if you've got this angle being congruent and this angle, and that is going to be the alternate interior angle theorem. So then you have two triangles that you end up with that are similar because they have two angles that are similar, and that's triangle DAB is going to be similar to triangle DEC. And again, you have angle theorem. So this is the angle here, and the angle from this alternate interiors and the angle from that alternate interiors. So this is the alternate interior angle. I'm sorry, this is the angle similarity postulate, where we say if we have two angles that are similar in a triangle, then they must, or that are congruent in a triangle, then the triangles must be similar. Okay. And then what happens is that means you can write ratios, and you're going to write the ratio that AB corresponds to EC. So these sides are the ones that correspond. So you can say AB over EC is equal to BD over CD. Okay. And it's written out there actually on line 10. And that's just because if you have two triangles that are similar to each other, then you can write ratios, and the corresponding sides are going to be proportional. And that's basically what you're going to say. The corresponding sides of similar triangles are proportional. And then you can rewrite that, and what you're going to do is just you take that and use a little bit of algebra. You multiply both sides by the denominators, and what you end up with is you have it written as an equivalent proportion. You should have AB over BD, so this side over this side is equal to the measure of EC over CD. And then because EC and AC are congruent, you can substitute, and AB over BD you can leave alone. So now all you're doing is you're substituting AC over for EC. So you had EC, and you're going to switch that one part out. So the difference between line 11 and 12 is the substitution property, and you've got that basic proof. But what is it really saying? It's saying that when you take and bisect an angle in a triangle, so that's what we've done. We've bisected angle A in this triangle, that this side gets bisected, okay, this BC side also gets bisected in a way, or not bisected, that's the wrong way to say it. It gets divided in a way into segments that are then in the same ratio as the sides. Okay, so this side and this side, you can see, I told the kids in the class, think about it like as though you were measuring somebody's effort, right? And you were measuring how much work they put in. And you thought about this guy over here, he put in a little bit of work, but this guy put in a lot of work, right? And then pretend that this line here is the profits, and you want to think about how much of the profit should they get. Well, if you bisect this angle, this guy earned this much of the profits. That's what that means. It's dividing it so that this side is directly related to the ratio of AB and AC, so that's his share, right? And this side is directly related to that ratio as well, and so it should get his share as well. So that's kind of the idea behind that angle bisector proportional side theorem. Okay, coming down a little bit on this one, talks about how you can apply that. So then again, it's meaning that since North Craig Street here is bisecting this angle, then it means that the ratio of Belfield Avenue to Ellsworth Avenue it's dividing Fifth Avenue in proportions that are equal to the ratio of Belfield Avenue over Ellsworth Avenue. And so you can solve for an unknown quantity. They give you some measurements in here. You fill in the measurements, and then you can write a ratio. Just look at this triangle to help you with this problem. Look at this triangle. Think of it exactly as this triangle, right? Right? Just think of it like that, and then write a ratio just like this one, just like that, what you could prove. And if you divide it into ratios, like if you write it into a ratio, all the measurements like that, you're going to have one missing side, and then you can use your you can use your skills, your algebra skills, to solve for what that side is. And here you have another exercise kind of like it. If this segment CD is bisecting ACB, then you can write a ratio. 24 over 8, or let's say 8 over 24 is equal to x over 30, and solve that. And here you would be able to do the same thing where you'd say x over 9 is equal to 22 over 11, and solve that. And then this one's a little trickier because this is a quadratic. It's going to end up being a quadratic equation, but you're going to say this unknown side x over 7 is equal to this unknown side. But what is this unknown side? We don't know, and you need another value for it. And instead of calling it x, we're going to call it, see, together they make 36. So we call AB, it could be 36 minus x, and that's what you'd put in there. So you'd say x over 37 equals 36 minus x over 14, and you're gonna end up with a quadratic equation that you're gonna need to solve. And then this is really straightforward: 6 over 14, x over 16. So just some exercise problems that you're gonna work on. Next one you have here, triangle proportionality theorem, and it says if a line parallel to one side of a triangle intersects the other two sides, it divides the sides proportionally. So that would mean DE is parallel to BC. Now this only works when DE is parallel, but if they are parallel, then what you can do is you can say this segment over that segment is a ratio where CE is a ratio that's equivalent. So again, we're going this segment here over this segment here, right, is a ratio that's equal to this segment here over that segment there. Okay, and what you're going to do is you're going to, because these are parallel lines, you're going to write a paragraph proof, and the point being that this angle, right, ADE, is a corresponding angle to ABC. So these two angles have to be congruent by the corresponding angles postulate. Same thing goes for the opposite side, where this angle and this angle are congruent by the corresponding angles postulate. Therefore, this smaller triangle ADE has to be congruent to or similar to this triangle ABC. They have to be similar, and the reason they have to be similar is because they have angle similarity. Angle. Of course, you could use the reflexive property and say angle A is similar to itself. And then basically they want you to go through and put this in an order, and I'm going to let you work your way through that. Everything is given, so you're going to start. I mean, everything is very doable here. You're going to start here. Just remember, when you're doing these kinds of proofs, is that you're going to think about, what does this mean, right? If you start out with that these angles are congruent, then what does it mean? And then you work your way through it. So I'm not going to take you through that right now. And then once you get it in order, you write it out in a 2-column proof there. Now the converse says that if you know that this segment over that segment is equal to this segment over that segment, then you know that the triangles are, or that these lines have to be parallel. They must be parallel. And what I'm going to tell you is that once you're done going through this one, this proof here, that's all the statements and reasons are given. You just have to put them together and put them in order. Once you get done, then you're going to go the other direction with it here, right? You're just going to basically go backwards, because you're starting with the, with what you were trying to prove before. Now you know that you can go back up from it and end up here. So it's basically going backwards through it. All right, now we have the proportional segments theorem. And so the proportional segments theorem, let me grab my little bit of notes here. What it's going to talk about here, it tells us to draw a line. So they want you to draw a line CD, and that would go through here, and they want you to label a point H right here that goes through L2. So you're going to end up with some triangles here, because these lines 1, 2, and 3 are all parallel. You're going to be able to take a look and figure out that, again, you're going to have some, using that same theorem, you're going to know that the sides are proportional. So the triangle that you formed here, there's a parallel line going through it, and that's a, through CDA, there's a triangle. And then, so the segment from BH and AD we know are parallel. Therefore, this segment over this segment is equal to the measure of this segment over the measure of that segment. So they're going to be ratios you can write there. And then what you're going to end up doing is you're going to use the transitive property, showing two things are equal to the same thing. So you use the transitive to prove that. Triangle mid-segment theorem says that if you connect the mid-segments of sides of a triangle, then the resulting segment, if you connect, I'm sorry, not the mid-segments, if you find the midpoint of this side and you find the midpoint of that side and you create a segment that connects those midpoints, that's called a mid-segment. And then the idea is that this mid segment is going to be equal, it's going to be parallel to this base of this triangle here. And also the length of this mid segment is going to be half exactly of the length of the base. And so I'm going to have you work through that. And let's see. You just need to read through these. Make sure you understand that concept. I would say that your big challenge here in proving this, I'll go back just a second, but there's a bit of algebra in here, and then what you're going to do is you're going to be showing that if you add these together, right, MJ and JD together, that it's equal to MD, which is the segment addition postulate, right? M to J plus J to D is equal to MD. And also the idea that because this is a midpoint, that MJ is exactly 1/2 of JD. And so that's going to help you know that this proportion here, right, MJ is half of MD. Therefore, and then you're going to prove that these triangles are similar, which is really simple, right, because you have corresponding angles of parallel lines in a transversal. And so those two angles are congruent, and of course angle M is congruent to itself. So triangle MJG is similar to triangle MDS by angle similarity. Therefore the sides are proportional. If the side here is 1 to 2, then this side here is 1 to 2 as well. It's half. If this is half of that, right, then this is, oh boy, then this is half of that. And that's really all you're trying to prove there. Okay. And then you have to prove also that they are parallel. And I think the point about them being parallel is that, let's see, we know that these angles or these triangles, we know these triangles are similar, and so therefore the corresponding angles must be congruent. And if the corresponding angles must be congruent, then the slopes of these triangles must be the same. And how do we know that they're similar? I think I told you that these are corresponding angles. That's a little unfair to do. Instead, what I'd say is that we know this pair of sides is proportional, right? This side is half of that side. We know that this side is half of that side, and we know this angle is congruent to itself. So by the side angle side similarity theorem, we know that if two sides are proportional and the included angle is congruent, then by side angle side the triangles are similar. Once you know the triangles are similar, then these base angles are also congruent. If the base angles are congruent, then then this is by the converse of the corresponding angles postulate, these line segments must be parallel. So you've got the parallel piece there, and then the ratios are 1 to 2, so therefore this is 1 to 2 as well. This is half of that. So that's kind of the way you want to go with that. I know that was a lot and kind of confusing. I'll let you read through here. If you understand that, then you should be able to do it. Here you're going to use that same mid-segment theorem to work through this problem. I'm going to let you just contact me if you have a problem with it. I think you should be able to do that as well. And it says determine the perimeter. So once you have that triangle created, you should be able to do the perimeter as well using the distance formula. And that's lesson 6.3.